are located in the world. And first of all, thanks for this great opportunity. I'm sorry I didn't send you a CV, so I'll just do it very shortly here now. I'm Bjarne Bøklepp. I'm currently leading advisor technology management subsurface data in Equinor, a Norwegian energy company with an ambition to be a leader in the energy transition. And now I need your help, Shivanandan, to you can make the first click. Yes, thank you. So the setting for today's fish is ultrasonic Doppler measurements while drilling. And even if well construction and drilling operations are commonly associated with the production of hydrocarbons from the subsurface, and also to be honest, this is still the main cash cow for the company and for the industry. But we also see drilling wells as part of the solution in the transition towards a low carbon solution future. For example, we're drilling subsurface carbon capture and storage wells, or CCS wells, as you might have heard of. Could be just regular water drilling wells, geothermal energy wells, or etc. To name a few examples. And independent of the purpose of a well, if it's intended as an oil or gas producer or injector or injector well or geothermal or for CO2 injection, the actual drilling process is much the same, and so are the risks and uncertainties associated. And the Deepwater Horizon disaster in the Gulf of Mexico in 2010 was an ugly example, and for the entire industry, a somber reminder of what could happen if we misunderstand, misinterpret, or overlook the data or the signals from the subsurface. And as operators, we are hence always on the outlook for new technologies and better processes, for safer and more efficient ways, of course, of constructing and monitoring our wells and operations. New ways of acquiring more and better subsurface data, new ways of processing, interpreting, and utilizing that same data, and ultimately to obtain a better understanding and management of the involved risks and uncertainties. And this quest is also very much aligned with and rooted in the Equinor strategy as is shown here on this slide. Always safe, high value, and low carbon is that's our non-negotiables. And just to emphasize, always safe comes first. And having a cross-disciplinary experience myself from within drilling, well placement, and first of all, petrophysics, I'm especially interested in tools and technologies bridging the gap between the different disciplines involved and the domains. And when I first pitched this idea back then called Ultrasonic Doppler While Drilling to the Equinor Blue Sky Innovation Council in about 4 years ago, this initiative was also approved primarily as an improved safety and drilling efficiency technology. And then secondary, it's regarded as a technology for improved cross-domain operational collaboration and subsurface evaluation. Click again, please. As the inspiration and motivation for the project originates from the medical ultrasound and through our participation in CEUS, a research and innovation collaboration. So the CEUS, or Center for Innovation Ultrasound Solution, is managed by NTNU, the Norwegian University of Science and Technology, as mentioned. And also that's where the Equinor Research Center, where I work, is happened to be in Trondheim, Norway. And also Svein Erik Måsøy, who is the center director of CEUS, is also participating in this meeting today. So we decided to run this project or this idea as a PhD study through CEUS, and Shivanandan has from day one been our excellent student, planner, and doer, and pretty much on top of everything. So, and as the project now is coming to an end, we are very pleased and excited to get the opportunity to present our good work and main conclusions here today. So thanks again for the opportunity. And by that, I think I'll just give the word to Shivanandan for the technical and interesting bits. Thank you.
Thank you, Bjarne. Presentation is broken down in two parts, essentially. The first part talks about Doppler, the use of Doppler for influx, efflux detection in LWD. So we'll talk about that in the beginning. And then towards the end, the second part talks about gas detection at the drill bits, of course, using ultrasound, but not Doppler. Let's begin with the first part, which is Doppler logging while drilling for influx, efflux characterization. Let's have a brief introduction of what is this influx. Maybe many of you know about it, some of you don't. So just a short recap. What you see here in the video is a typical drilling operation. You see a drill string drilling through the formation, and you see a drilling fluid that is usually pumped in through the drill string, and it carries the cuttings and rock chippings back to the surface. It's usually recirculated in a closed loop after filtering, etc., on the surface. But essentially, it's a managed pressure drilling. So the pressure of the drilling fluid is carefully managed to be in balance or slightly above pressure from the formation, so that the drilling proceeds normally. As one might think, it's normal to have a lot of fractures in the formation. You see several of them in this figure as well, but these can be drilling induced or also sometimes naturally existing. Depending on how the pressure balance between the formation and the drill string is, you might encounter situations where the drilling fluid loses out into the formation. What you see, something like what you see in the video. If the pressure imbalance is, for example, reverse, then you might also experience a formation fluid influx into the borehole. Now, both these situations causes disturbance in the pressure balance of the drill string, of course, and that has to be continuously managed by the drilling operators. And in case of some situations where the situation goes out of control, where you have a sudden influx of a large volume or a sudden efflux, either way, then you have you have, first of all, a loss of drilling fluid, which is a very expensive fluid. More serious situations where the pressure imbalances are not adequately controlled can lead to a situation called as kicks, and that's essentially a sudden loss in pressure in a sudden loss or sudden gain in pressure in the wellbore, and that could lead to a loss of the wellbore if again not contained in a timely manner. Worst case situations, of course, like Bjarne mentioned, is a blowout, the Deepwater Horizon, and there have been also many other blowouts, but the Deepwater Horizon is an infamous one. So in the worst case scenario, you can have a blowout. It is essentially an uncontrolled release of hydrocarbon on the oil platform, and that is associated with a tremendous amount of environmental damage, safety, human loss. Not to mention the borehole, the entire boreholes are lost. So that's something which everyone is interested in preventing, and that's where our project comes in. The inspiration for this project is, of course, since we're working at the innovative ultrasound solutions, which is of which a large number of projects are driven by medical ultrasound. We have Doppler ultrasound, which has been used in the medical industry for several decades now, and it's a very established method for quantifying blood flow in the human body. You see color Doppler video down here, which is flow of blood through one of the blood vessels in the human body. And if we can do something like this in the human body using ultrasound, can we do something very similar in boreholes, where we have a very similar situation, yet with its own challenges, of course. We have a drilling fluid which is being circulated, and we might have loss of drilling fluid or gain of formation fluid, gases, etc. So can we use something very similar in the drill string to characterize such flows? Of course, the impact of that is very obvious. We have improved borehole stability that leads to safety of the drilling operations. We can identify whether the influx is a gas or a liquid and take adequate, operators can take adequate action according to that. And of course, it allows us to detect gas kick situations at a bit, so instantly as it is encountered without any information loss. Consider that these drilling operations may sometimes be occurring several kilometers subsurface, and any information that is gathered takes quite a lot of time to reflect on parameters, operating parameters on the surface. So this might as well give us at-bit information. Now, interestingly, many of these, or most of these drill strings or borehole drilling assemblies, as they are called, have ultrasonic logging tools mounted on them. And these are used to image the boreholes while the drilling is happening. It is interesting to see if we can use the Doppler processing on the exact same instrumentation without any modification. So then there is no entry barrier to using these or implementing these technologies. So the project, the PhD project that I executed essentially was to explore this feasibility. Can we do Doppler while drilling on the existing LWD transducers without any change in instrumentation? And if we can do that, what are the constraints to what amount of information can we gather? And that is something that we'll see in the presentation today. And before we move ahead, it's important to see the differences in the ultrasound transducers in the medical domain and in LWD that we will be using. So, of course, in terms of frequency, we are talking of much lower frequencies and much less sophisticated transducers. For example, single element transducers working in pulse echo mode, as opposed to several array elements that are used in medical transducers. 64 is pretty typical, but then you have also many advanced transducers that can have as much as 4,000 elements. Then, of course, the last bit is the very challenging drilling conditions. So you have the drill bit rotation and motion, vibrations because of the drilling operation itself. You might have eccentricity, and all these things complicate these measurements. And we'll see how Doppler fares in these situations.
Quick question.
Yeah.
So what precisely are you transferring from the medical application? Is it just software or a certain kind of device or an algorithm for the analysis?
It's essentially the knowledge of Doppler ultrasound for quantifying fluid flows. We are transferring that knowledge and that processing, the signal processing that is used in medical ultrasound. We're transferring that to single element transducers like the ones that are used in boreholes. And
okay, so it's pretty high level and general. It's not. I got it.
Yes. Yeah.
Thanks.
So before I move forward, I'd just like to give a brief on Doppler theory. I think most of you know about this, but I won't spend too much time here. But just to give a hint on what we are trying, what we are doing, or what kind of processing we are doing. Essentially, Doppler involves gathering backscatter signals from suspended particles in the fluid, right? And these backscatter signals, of course, are very weak in nature. And we are trying to see if what we quantify is if there is a fluid flow, the suspended particles move along with it. And if you have an ultrasonic transducer that is constantly pulsing acoustic waves into this fluid, we will observe essentially a shift in the arrival time from these backscatter signals. And then we essentially quantify the phase shift for each depth that we're interested in, or each sample volume. And if we look at that phase shift in the Fourier domain or in the frequency domain, then we can essentially identify high frequency components which are attributed to the fluid flow because of these backscatter signals. And you also have some low frequency components which might be because of stationary objects in the environment, also lateral flows, etc., which we call as a clutter, and we try to filter it out. But then using this frequency at the high frequency flow components, we can essentially calculate fluid flow. It's pretty basic in that sense. Yeah, coming to the drilling conditions, and those are some of the conditions that we mentioned or talked about in the slides before that have definitely an impact on or impose limitations on the Doppler processing, or rather the information that we can extract from Doppler processing. The first one of that is, of course, velocity limits. So it puts a cap on the maximum and minimum velocities that we can estimate. The upper limit is, of course, because of the sampling rate or the sampling rate of the hardware, the PRF essentially, and that is you can see that in the blue curve for various typical frequencies in LWD. The only way to increase that is essentially increase or decrease that is to essentially play with PRF, which involves playing with the instrumentation. The lower limit is then is induced because of the annular flow, so which flows in the perpendicular direction to the transducer, which is unavoidable. And depending on how the drilling operations are, at what stage the drilling operations are, we might have different velocities. So for two typical mean and max velocities that we know from literature, slow moving or low frequency signal that we see in the Doppler spectrum, which we have to inevitably filter out if we have to gather information from the backscatter signals from the high velocity flows. And because of that filtering operations, we lose any information or any velocities that might be in below these limits. The second limitation is again is because of pulse length of the ultrasound that we use for the Doppler acquisition. Again, pointing out to the fact that we are looking at very weak signals because of the backscatter. We need to use long pulse lengths, and it is very typical to use 8 or 10 wavelengths worth of pulse length in typical Doppler acquisitions in the medical domain, for example. And that kind of pulse lengths would put a severe handicap if we use it in drilling operations. For example, if we use a 1 megahertz transducer, we will have a pulse length which is about 15 millimeters long. And if we look at the borehole geometries, we would have anywhere between the typical spacing between the transducer and the borehole wall is about 15 millimeters, or at max about 50 millimeters. But on an average, it's about 20 millimeters, 25 millimeters. So if we have a dead zone of about more than half that depth, it's essentially a lot of lost information. When we did our experiments, we were able to tune the algorithms so that we could achieve a reasonable signal-to-noise ratio with about 4 wavelengths in 1 megahertz, of course. And the third most important influence on Doppler processing comes from the motion of the drill string. Now the drill string is rotating circumferentially, having a velocity of about 1 to 4 revolutions per second, which is a very high rotation speed. And the Doppler, the acoustic transducer, the ultrasound transducers are mounted on these drill strings, on this drill string. So then the transducers are also rotating at that same velocity, and we need to acquire signals at while the transducer is moving that fast. Then you also have axial velocities while as the drilling is progressing through the formation. These are very low velocities, so have very little impact on Doppler processing as such. And you also have eccentricity. So essentially, the drill string might not always be aligned with the central axis of the borehole, which is natural. It might be eccentered in most of the cases, and we need to account for that as well when we are doing the Doppler processing. And if we try to calculate some figures under these conditions, it puts a limit on the maximum and minimum pulse repetition frequencies that we can use, depending on the geometry and the rotation speeds. So what we see is essentially for a 6 3/4 inch tool rotating at typical 3 revolutions per second, we need to use at least about 15 kilohertz as a PRF, which is typical for many ultrasound instrumentation. And in such situations, we would end up with a scan resolution, an imaging resolution of 16 millimeters. So each pixel would be 16 millimeters, which is very low resolution, if you can imagine. Putting all of these constraints, so we can just put some ballpark figures on what kind of velocity limits that we arrive at, that you see in this table here. Okay, moving on. We first started with some very simple experiments with using water, of course. Didn't start with drilling fluids. We did that later, but we started with water. We made a very basic flow setup, something like this. We have a bucket filled with water, which is circulating it into a flow cell, which you see right here. And we have ultrasound transducers mounted on a robot, which is scanning through the flow cell. You see a small plate down there. We introduced different fracture shapes. You see simple ones here. We we use some more complicated ones later. We'll see that in the future slides. But then we put these kind of fracture shapes to simulate the fracture shapes and pump fluid through it to emulate the influx, or suck fluid out to emulate efflux. And then use Doppler processing on these transducers. So the one you see here is a 1 megahertz transducer. We also use 500 kilohertz for some experiments. But then these are the typical results that you are, or this is the typical way that you would essentially see the results essentially. So this is a Doppler spectrum on the top, where you see across its depth. So at 45 or 50 millimeters depth, that's where the fracture orifice is, and at 0 mm, that's where the transducer is. That's the convention for all charts and figures that you will see henceforth in the presentation. And you can see the full spectrum of velocity components that exist at each depth. And that is the kind of information that the Doppler allows us to get out of such influx situations. And you
What's
see
the
also,
color?
Yeah, sorry.
Sorry, what's the color?
The color is the signal strength. It's in decibels.
Thanks.
Sorry, I missed that. So it's in decibels. So at the maximum, you would have, in this case, SNR of easily about 30-40 dB at least in this image. But yeah, we are doing this with water. We'll see when we in the future slides. I'll show you some experiments where we did with real drilling fluids, which are extremely attenuative, and then the SNR is nowhere as strong. But then we'll come to that in the future slides. You can of course extract whatever information you want. You can extract the mean velocity, the maximum velocity, etc. What you see on the figure in the below is a mean velocity extracted from this spectrum, and that across the entire depth. Similar figure for another flow velocity, and we repeated experiments for the same flow rate for several times to see what kind of standard deviations in the estimates we are able to achieve. And we saw that the standard deviation is pretty low, about 0.05 meters per second in that terms. And in flow terms, it turns out to be about 4 milliliters per second. So it's extremely, Doppler has the possibility to quantify very small flows or influx, efflux through these fractures. Of course, since we are scanning across through the fracture, we can stitch together all of these Doppler spectra and obtain three-dimensional visualization of flow, something like this. What's also possible to estimate from these flow profiles is if we slice it through a sample volume very close to the orifice, we can estimate the shape of the orifice itself. And that allows us to get much more information on what kind of fracture it is and what kind of flows is happening. You can see for these two fracture shapes that we saw, we were able to estimate it very beautifully. There's of course some deviation or some error in the lateral measurement, and that is because of the point spread function, which is something which we cannot avoid. But when we compare it with the conventional pulse echo methods that are being used for imaging the boreholes today, when we apply it on the same flow cell for the same situation as these are subject to, we see the dramatic difference in image quality that we can obtain when we have a fluid flow. Yeah, these are the errors that I talked about quantified, but yeah, and then this lateral error is because of the point spread function, which I talked about. But then, yes, we can improve it further, and we tried some machine learning algorithms to do some super resolution imaging for that issue. We'll see that in future slides again. Okay, moving on to some more complicated experiments with actual drilling fluids, which are quite messy to handle. Essentially, we had to upgrade our flow setup to something like this, to a much more industrial scale to handle those drilling fluids, the pressures, etc. And this is what it looks like. It's a replica of the earlier flow cell, just a much more rugged version of that, zoomed in view. And we're able to, in this cell, we are able to have two fluid flow directions. So we can also pump in fluid in this direction, which is the annular direction, which is the regular direction where you would also expect in a borehole. And in addition to the regular annular flow, we can have an influx or efflux when we can push in or pull fluid out from this this location here. And then we introduce some more complicated fracture shapes here to see how Doppler fares in estimating the shapes of these fractures. This was specifically done for the machine learning part to estimate how that performs. But then you see some 4 fractures that we tested out in this case. And we used several drilling fluids, 5 of them, which covers most of the ranges that are commonly used in the field. So we use the water-based muds and oil-based muds, which are the most common types. You also have some synthetic muds, but those are used for much more specialized situation. These are used most commonly, and it also covers the full spectrum of densities or mud weights, as they call it, in both cases. So stretching out from the lighter 1.2 standard gravity muds to the heavier 1.7, 1.8 kind of standard gravity. And yeah, just to let people who don't know about drilling fluids, it's that these are extremely attenuative fluids and very bad to work with for ultrasound. We'll see that in these slides. So when you look at the acoustic properties, for example, sound speed of the drilling muds or something like this, the red curves here, split across the water-based and the oil-based mud. But then what's interesting to see is the attenuation. And this is the attenuation per centimeter for 1 megahertz. And you see for the lightweight muds, it's about 2 decibels for every centimeter. But then for the heavier muds, it's anywhere about 5 decibels. And for oil-based muds, it's even worse. It can go all the way across 8 decibels per centimeters. And if you're looking at imaging about 50 millimeters worth of looking through 50 millimeters worth of drilling fluid in a typical situations in drilling, that means the sound has to transit about 10 centimeters or 100 millimeters two-way to come back, right, in a pulse echo mode. And that leaves us with a very high amount of attenuation. So 8 decibels would turn out to be 80 decibel loss in signal. And again, putting that in perspective, that we're looking at backscatter signals, which are already weak in nature, it's much more complicated. Or much more difficult, rather. This is moving across, starting with the lighter muds. We try to look how the Doppler images look like for all of these different shapes. You see them here. Of course, we can no way identify the shapes just by looking at the Doppler image. It's just a smeared out version of what the actual thing is. But then that's where the machine learning comes into. We'll see that later. If you look at the flow velocity for, or try to estimate flow velocity from all of these fracture shapes, while changing the annular velocity, the annular flow velocity. So we tried to see if that has an influence. We already know that Doppler can estimate these velocities without any problem, but if we have additional annular flow moving perpendicular, does that affect? So if you see here for a 50 liters per minute annular flow rate, these are the flow profiles. And if we increase it or almost double it to 80 liters per minute, this is something, the velocity profiles look something like this. So we see that it's the annular flow doesn't really have that much of an impact on the velocity estimates, either on the mean velocity or on the standard deviation of the estimates for each sample volume. So it's, at least we can say, between these limitations, between these ranges, the annular velocity has virtually no effect on Doppler estimates. Looking at efflux, so when we suck fluid out instead of pumping it in, again, for both these conditions, we are still able to estimate the efflux velocities quite reasonably. If you compare that, you might observe that comparing it with the flow meters, which are these pink lines, the estimates are quite far off, and that is to be expected because with Doppler, we are only estimating, we are only able to estimate the axial or the flow velocities at 0 degrees to the transducer. Right, since we don't know, we don't have an independent angle measurement of the flow streamlines. And in case of an efflux, it's a sink flow. So you have very high, components of which are horizontal in nature, which will not be, or rather contribute to the clutter of the Doppler signal and not be estimated or be severely underestimated at least. And that's why we see that the velocity estimates are much lower. In this case. So yeah. So if we look at how we talked about how the attenuation values, we saw the attenuation values, but how do they look like when we take a Doppler image? And if we put in terms of the signal to noise ratio of these Doppler images, this is the curve that you see. So the blue ones are for the water-based muds and the red ones are for the oil-based muds. So with the same 1 megahertz transducer and a 4 wavelength pulse length, we see that the SNR, as the depth increases, drops dramatically. It's quite okay still for the lighter water-based mud. We still have an SNR of about 20-21 dBs, so it's fine. But for the heavier muds, the SNR in the water-based mud drops down all the way up to about 2-3 decibels, which is pretty low, but still okay for estimating flow velocities. But the problem comes in when we look at water-based muds, where we have total loss in SNR. We cannot estimate anything. So the SNR drops below 1 right after about 32 centimeters in the millimeters in this case. For the heaviest mud, we have no signal penetrating anywhere after about 15-16 millimeters.
Sorry, could you explain the, I'm sorry to interrupt so much, but what's the acquisition geometry? Where are the sensors?
So the sensors are at 0, and the flow orifice, the fractures are at 50.
So how do you get all these points as a function of depth?
We can acquire, so when we acquire Doppler spectra, we can acquire the spectra at each sample volume. So each point that you see on this is one sample volume, which is approximately equal to one pulse length. And if we take out the Doppler signal from that individual pulse length, we can take the power of the Doppler signal there and build the Doppler image. And then I use that image to calculate the SNR. So we have the signal where the orifice is located at, and everywhere in around far away from the orifice is where there is no flow. So that's the background level or the noise floor level, and the SNR is the ratio between the plot. What we plot here is the ratio between the power levels in these two regions.
So you get depth somehow sort of from the time delay from the return signal.
Yes. So we have backscatter signals from each depth. So it's a pulse Doppler acquisition where we have several transmits. So we have we essentially have a fast time and slow time signal which has several frames, and then you can take out slices at each depth and then calculate and then estimate the Fourier spectra, the Doppler spectra.
Thank you.
Yeah. So so the problem is if we want to estimate these fluid influxes or effluxes, we need to be able to see the Doppler spectrum at this sample volume, at the sample volume which is immediately before the fracture orifice. And that is not being possible with the 1 megahertz transducer and the setup that we use for the water-based mud. And in that case, we had to go down. We had to either increase the pulse length to twice the value, or at least we had to go down in frequency. And we did both of that for getting meaningful signals from the heaviest water-based mud. When we use the best values for best configurations for each of those flow muds, then this is how the Doppler signals look like for each of those, for the same fracture, but then for different muds. And we see that this SNR even is still very low. For the heaviest muds, we have SNRs of 1.3, 1.1 dBs, which is barely above SNR of 1, which is the minimum requirement for estimating anything. If you have anything below SNR 1, then things become very challenging to estimate anything, right? So we see that we are able to get at least some meaningful signals with that kind of a configuration. And putting all of those together in a bar chart just to visualize how things are in terms of the signal to noise ratio, in terms of the depth of penetration, and the attenuation itself. We already talked about all of these things in the previous slides, but just to put in perspective. Okay, moving on to the fracture estimation or the fracture shape estimation. We try to use a very, again, there is some knowledge transfer from medical ultrasound, where a colleague of mine also doing his PhD on medical ultrasound, on cardiac ultrasound, was working on a similar problem, trying to estimate the shape of the leakage in the cardiac valve when we have abnormal flows. So it's very similar, but where we try to develop the residual network and try to estimate the shape of the leakages. So these are some laboratory experiments which he did, and try to estimate. The triangle ones are the ones from the neural network. The white ones are from conventional thresholding that you would apply, which is generally applied in the industry. So it's a very basic residual network where we generate a lot of simulated fractures and try to generate Doppler signals using Field2. It's a open source a citation-wares platform for simulating ultrasonic fields. We try to input all of the parameters, all of the conditions of the transducers that we know about, and try to generate Doppler signals, which are very close to what we get from the experiments, the experimental flow cells. And then try to train with both these information, the information of the shape, the actual shape, and the Doppler image, and try to train the neural network for thousands of such images at different signal-to-noise ratios, and try to minimize the loss. The train network, when we try to use on estimating the fracture shapes, so you see for 2 of these shapes, we see that the neural network is able to improve the estimation of the shape significantly, quite significantly. When we compare that with the regular thresholding approaches that we would apply, we see a marked improvement in the estimates. For various fracture shapes, so at least we had 4 fracture shapes which we had in the experiments, and if we plot out several experimental frames and try to estimate them in all of them, this is the performance that you see. The blue curve would be the performance of the conventional thresholding algorithm, which is this, the 3dB approach. And the neural networks are these box plots. So we had 2 versions of the neural networks, one with without black box noise injection, and the other one we added some Gaussian noise, which is not very well explained, but somehow that tended to improve the variance of the estimates.
Question.
Yeah.
Why is the right-hand lower image tilted opposite to the left-hand lower image?
Oh yeah, no. Say again. This one is tilted opposite. So sorry, it's just my mistake. So when I'm imaging these, it somehow took a flip. So I just have to flip the image across.
Okay, thank you. So it's not that I disagree. It's
looking
just flipped.
Yeah, sorry.
Thank you.
But these are, both of them are the same shape. So this image just has to be flipped the other way around. But yeah, so the application
actually both images. I'm sorry, Doug. Actually, if you look at the top image as well, it is flipped also.
Yes, it's also flipped. So vertically, it is both of these images are. These images had to be flipped across, but yeah, since I had I used 2 different softwares. This one was done in Python. This one was in MATLAB. I didn't realize that, but yeah, sorry for that. But then, yeah, the idea is that the neural networks are able to outperform at least the conventional thresholding approaches, and then this can find applications in not only fracture imaging in boreholes, but also other applications in boreholes. For example, well perforations in production logging, for example, and also we acquire a lot of conventional pulse echo images, and these are of very low resolution because of the rotation speed we saw earlier, 16 millimeters, that kind of poor resolution. So if we can probably readily use such neural networks to improve the segmentation in such low resolution pulse echo images as well. Yeah, that was the Doppler part. The next part is about gas detection. It's still ultrasound, but not Doppler. I'll try to give a brief context on what this is and what the gas is we're talking about. So it's still drilling in formations, and it's still formation fractures. But while we're drilling through the formations, the formations always has gas pockets. It has gas in the rock itself, and also might have isolated gas pockets which are having much more volume of gas. And of course, these rocks are crushed as we drill through, and gases are liberated into the drilling mud, into the drilling fluid. And this is a severe problem because deep down, when you're drilling at a very high pressure and temperature, the gases might not cause much of a problem. But as these gases rise in height, they will expand because the pressures are lower, and then they start expanding, and then you have sudden expansion at places where you have where you reach the phase boundary limit. And that is a problem. So to be able to detect these gas influxes at the drill bit itself is quite useful. And we stumbled upon this while doing the Doppler experiments, that we could also estimate or detect at least gas bubbles. So we will use a term called gas volume fraction in the slides that you'll see henceforth. But the gas volume fraction is something that is used in the industry. It's just a proportion of the influx gas to the volume of all other fluids in the borehole. We express that in terms of percentage, of course. And current methods in the field are all involving mud gas analysis at the surface. So the gas has the gas in the drilling mud goes up to the surfaces and we have a phase separation there, and you have gas analyzers who try to analyze what kind of gases and what amounts are coming in. But then if you have a sudden gas influx at the drill bit end, then you have to wait at least 25-30 minutes until this gas reaches the surface. And if it is too large to cause a problem, then that's a problem we don't want. There have been many methods that have been proposed in literature, at least. We're not sure if any of them are being used in the field as of now, but many of them work on attenuation measurement and speed of sound changes of the drilling fluid because of this gas influx. We try to take a different approach and try to use backscatter, because this is what we stumbled upon when we did the Doppler experiments, which is again working on backscatter. And we find that, of course, gas bubbles are air-filled bubbles, which are extremely strong scatterers of ultrasound. And then we can quantify these backscatters. These methods are also being used in medical ultrasound also for emboli detection or blood tissue, stray tissue in the bloodstream. And you see, again, like I said, sharp, in case of presence of such emboli, you see a sharp increase in the signal power because of these emboli, because of the strong backscatter. We made a very simplified setup. You can see here, we have an ultrasonic transducer here, a drilling fluid. Again, in this case, the experiments were done with water. And we have a venturi nozzle with an air influx, airflow meter, which allows us to calibrate the amount of air into the venturi nozzle. Essentially, it is used to collapse the air bubbles, which is injected into it, so that we have very small air bubbles coming into the flow stream. That's the actual setup, photograph of the actual setup. Now, when we start measuring the backscatter signals from this fluid, case one is when you have no gas bubbles, of course. So then you have a clean signal which has nothing, no information. It's just a noise floor. When we start injecting very small amounts of gas, so 1% gas fraction in this case, we start seeing these sharp, high intensity transient peaks. And these are, of course, because of these bubbles, because of the backscatter from these bubbles. Increase the gas fraction even further to about 10%, then we see that the signal is all saturated with gas, because then you have a huge population of bubbles in the acoustic beam. It's easy to quantify. There are various ways to quantify the amount of gas or the presence of gas in the bubbles. But we found that measuring the skewness of these signals tended to be the most robust method, at least to be able to quantify or classify between no gas and very little gas. There are other methods which were able to do that as well, but then the separation between 0 and 1 was the highest, at least that we observed when we measured the skewness. So when we see that if you have a clear signal without any gas, you have a very low skewness, of course. With very small amount of gas, you will have some transient signals, and that of course changes the skewness to a very high degree. And then when the signal is again saturated, the skewness comes back to lower values. If you do a lot of experiments and try to see or statistically try to see how they look like, this is how we look at. So between no gas and very little gas, we have a very high separation in skewness, and this can be used very easily in the field. This was at a signal to noise ratio of 26 dB. If we drop that SNR by about 6 decibels, so half the amplitude, then even in such cases, we see that the separation is quite large. So although there is a drop in the range, but it's still pretty large. But is there also an opportunity? That's about detecting gas, but is there an opportunity also to quantify? And there have been many papers that suggest that it is possible to quantify with various methods, also using backscatter. We tend to differ on that sense, and that's why we try to explain here. So if you look at the same gas volume fraction, so if we fix the gas volume fraction, in this case, in these three images, it's all 4% gas fraction. But if you observe these images carefully, you'll notice that you have a much more number of bubbles in this third image compared to the first one. But then all of them are still the same gas fraction. What's different is that the size of the bubbles in this case is much smaller compared to in this case. Right, and because of the size of the bubbles, the acoustic signal, the backscatter signals that we would obtain changes also significantly, and all of these are still for the same gas fraction. So if we look at or try to quantify that, we try to see some theory on the acoustic attenuation. It's basically two phenomena. It's absorption and scattering. Absorption is of course material dependent because of the viscosity, thermal conductivity, etc. is the material property of the fluid. We can assume that to be same as long as the drilling fluid is same. So let's say that does not change. But what does change is the scattering part, which is because of these gas bubbles. And if you have more or less gas bubbles or gas bubbles of different sizes, then the scattering coefficient will change quite dramatically. There are various theories to explain these scattering intensities. Some of the more widely used, one of them is Rayleigh scattering. So when your bubble sizes are extremely small relative to the wavelength, then you would probably experience a Rayleigh scattering, which is expressed by this equation. But then the important parameter is that it's the 6th power of the size of the bubble. For much larger bubbles compared to the wavelength, then you have something called as a specular scattering, where then the intensity of the backscatter is proportional to the square of the size of the bubbles. There's also, of course, also other theories that can explain the scattering intensity for bubble sizes which are very close to the wavelength, but we ignore that for the time being. When we try to compare or combine both these, so take a ratio of these scattering intensities, we see something like this, and we see that we have the ratio turns out to be approximately 1 at lambda by 10. So suggesting that at this bubble sizes, you have equal contribution from both the Rayleigh and specular scattering. So we would want to use the Rayleigh scattering theory to explain the scattering in this size domain. So the larger size domains, we would want to use the specular scattering theory. Okay, if we combine this, if we translate this into gas fraction estimation, then it looks like something like this. So gas fraction is not, if we look at in terms of number of bubbles, it turns out to be inversely proportional to the cube of the size. And we combine that with the scattering theories. Then for Rayleigh scattering or very small bubbles, the signal backscatter coefficient or intensity of the backscatter would be the 3rd power of size. Whereas for specular scattering, it will be inversely proportional to the size. And this is something which is not so intuitive and not so easily found in literature as well. So in this case, if you have lesser bubbles, the intensity will be actually higher. Or sorry, the smaller bubbles will have a higher intensity. Okay, if we combine this and try to see some realistic situations where we have a large amount of bubbles, but then we still know the size fraction of the bubble, or we still know the bubble sizes, or at least the distribution of the bubble sizes. In such cases, we can easily add up both these theories and try to estimate the intensity of the backscatter signal. And that is something, it looks something like this. If you simulate or experimentally observe, it's quite the same. So you can estimate the bubble fraction with the intensity of the backscatter signal quite easily. And this suggests that you can quantify gas fraction just by knowing the intensity. Medical ultrasound, they use a lot of contrast agents. And there also the bubble sizes are quite, or at least the distribution of bubble sizes are quite accurately known. So in such cases, it's quite easy to use the power of the backscatter signal to quantify how much amount of gas bubbles are there. But in a borehole scenario, that is not so true. So most studies stop here because it's possible here. It's also possible in boreholes, but it's not so true because there the size fraction of the bubbles is not known. Our size distribution is totally unknown and can change dramatically from time to time. And in such cases, if we try to put that into the equation and we see make the size fraction totally random, In that cases, irrespective of what the gas fraction is, the intensity of the backscatter signal gives us no information on what the fraction is. So it's impossible, or it's not possible to estimate gas fraction just by using a backscatter intensity. That's what we conclude with this study. And we also observe that in experimental situations. The experimental one is much more, we had much less control on the gas bubble sizes. So of course you see a much lesser spread in the values, but the message is clear. Yeah, thank you for listening. Most of the work that I presented here have been presented at various conferences. We have links to those presentations if you want to look at them in more detail, and most of the work is published. 2 of the papers are already published here. The third one is under review. The fourth one on the mud experiments is, we have the draft, and we will be submitting it in a few weeks. So most of it is open source. I can send these links once they are available, of course, but thank you for listening, and open the floor for questions.
Thank you. Thank you, Indimath. Thank you very much. Any questions?
Well, I'll venture a question. Thank you for a very interesting talk, and it's quite challenging to turn these laboratory demonstrations into practical downhole solutions. To ask about bubbles, there's 2 major field application areas where bubbles are relevant. One is the drilling safety, where lost circulation is going to lead to bubbles flowing up the annulus. An easier context is reservoir monitoring, where there may be bubbles being formed as production fluids are flowing up. But typically the bubble fraction it goes from near 0 to something significant well up the way, and there are telemetry issues. Do you have a vision for how to get telemetry for this at the bit analysis? And also, it would seem that trying to use some of these methods first in an environment such as reservoir monitoring, where they could be demonstrated, might be a practical middle step. That's a lot of talk in one question, but what's your vision for going from these laboratory demonstrations to commercially viable things?
It's a very interesting and valid question that you ask. So for one, the bubbles, when they flow into the formation, when they flow into the borehole, they would not be gas bubbles, right? They would not be in the gas phase. They would essentially be in the supercritical phase, and they are dissolved in the drilling in the fluid itself. So they are still liquid and not gas. And then in such situations, we would not be able to get any backscatter signals, right? And we essentially want to be able to detect these at that point. Now, once we are able to detect it at the bit end, then telemetry itself is, I don't know, I don't see that much that much of a problem, because even with the existing methods, you're able to, if you're able to say, hey, there is some amount of gas and we detect something, then we're able to get that information through telemetry in a couple of few tenths of seconds. So it's not really that much of a problem. It's still the message travels at the speed of sound, right? But yeah, being able to detect it at the dissolved gas stage, that is something which needs, of course, further study. And what we show now, that if it is in the bubble form, then we are able to quantify it, or we are able to detect it, which is quite easy. But to be able to detect in dissolved phases, we have to think of methods where we can sort of evolve the gas bubbles locally. And that has to be explored. And if we are able to do that using some tertiary method to be able to evolve those gases at the bit end, and then we can use the acoustic tools in conjunction with that method to be able to see or detect those gas bubbles. Bjarne probably wants to pitch in.
Yeah, I could comment on a few things there. It's a very valid question, and as you say, it's early detection of if you have gas influx is critical. And today's challenge is that if it's in pressurized state, you actually have to circulate it up to the surface, and sometimes even get it back out at surface before you detect it, and then it might be too late. So that is why partly we started to look into this. Can we actually detect gas influx even if it's in a pressurized state? And about the telemetry, absolutely, you are onto something there. And today we are limited by the mud pulse telemetry, which is in the order of a few tens of bits per second maximum. And we are moving more and more over to standardizing what is called a wired pipe, where you are now at around, I think, 50,000 bits per second. So it's at least a times 1,000, and we'll see more and more of that implemented. And that means also we can transmit more and more data in real time at a much higher rate, and also to include new types of data and more high resolution data that we haven't done before. So I think that we are approaching very interesting times with that technology, because that has kind of been developed hand in hand with or over the last few years.
If that's true, that's a very interesting development. I'm sure it was in the 20th century when I first heard technical talk about wired drill pipe.
Okay, Zhang, you have a question?
Yes, hi. Thank you so much for your presentation. So you started by saying that the approach doesn't require new hardware because the hardware already exists. And you showed some lab experiments to, to show that this approach might work. So my question is, I believe there must be a lot of field data. There must be a lot of data that's been already collected in this from LWs. Have you looked at actual real field data and seeing if you can get something out of that data?
Yes, so it's true that what we talk about, it doesn't need any change in hardware, but it needs a change in the signal processing and the acquisition. So because Doppler, in case of the regular pulse echo imaging that is done, it's usually a few frames or few pulses at each depth, which are then averaged to get the amplitude information at the or develop the pulse echo image. That is insufficient to develop Doppler acquisition. For Doppler acquisition at each point, we will probably need about 100 to 150 signals at each point to be able to quantify flow. So in terms of the hardware, there doesn't have to be any change, but in terms of the acquisition, so we need to acquire data in a certain format to be able to do Doppler processing.
And that has not been done yet?
Yeah, yes, that format of data is not available, at least from the data sets that are there.
So you have not done testing in the field,
no,
I guess.
Not with the field data, no. So this is we did a feasibility in the lab scale, tried to emulate conditions that might exist in the field in the lab, try to do it as much as possible. But of course, there are more challenges and more detailed studies are required. So yes, that is something that has to be done as a future work for this, the next step.
So just to follow up, if you allow me, I may. So to do a field test, basically, you need to tell the person who's making the measurement to acquire more data. Is that something feasible? Is that can be done currently? Can be asked for?
Yes.
I can respond to that. So we have looked into that now and then, but it hasn't been done extensively. And the thing is that most of these tools, especially on the LWD side, they are set up so they do not record the actual full waveforms because they will fill up the memories too fast. So typically they acquire the waveform into just intermediate memory, and then you just store the first arrival time and the amplitude. So that's basically all of the raw signals that we're left with.
I see. I see. So there is, maybe there is some limitation in hardware in the sense that, you know, the memory and any other things as well, probably. Well, thank you so much. I really appreciate
it. But we can still, it's always possible to actually at least modify the algorithms that are being run at the LWD tools, which doesn't require any hardware changes. It's just a software update. And then do the position. So yeah.
So you're basically doing a calculation on the edge, what they call nowadays.
Yes, exactly. That's what they do.
A little processing that does it while it's acquiring.
Exactly. Yeah.
Yeah. Well, I look forward to that. It's very interesting. Thank you so much for your presentation. I appreciate it.
Thank you.
I have the question. On your experiment to detect the influx and the outflux, the distance, I mean the 50 millimeter distance, that is a vertical distance between the sample or the fracture with the transducer, right? That is a not the horizontal distance.
No. It's the distance between. So is the distance the transducer are mounted perpendicular to the axis of the drill pipe. So it's the distance between the transducer and the borehole wall.
Okay.
It's the annular distance.
Okay. So
the 50 millimeter is kind of a worst case because you will assume that you might have eccentricity in the drill string when you're drilling. And in case of extreme eccentricity, then you might end up with about 50 millimeters kind of a distance. But on an average, it's usually about 20 millimeters. That's kind of the ballpark figures.
So for the oil-based drilling field, the attenuation is so strong. So when distance is a 50 millimeter, the ultrasound energy almost absorbed by the drilling fluid, right?
So that's what we see here. And maybe if I can move to the earlier slide, give me a second. Yeah, this is where you see the for so for the oil-based mud, the heavier ones, then you see that most of the sound is absorbed within about 17 millimeters. But this is for a 1 megahertz probe. So if we drop it down to 500 kilohertz and double the pulse length, so instead of 4, you go for 8 wavelengths. So in that case, you have a larger dead zone, of course, but then you're able to penetrate the signal all the way through. And in that case, then you see the Doppler image here. So using a 500 kilohertz and an 8 wavelengths, then you're able to obtain a meaningful signal to noise ratio at the 50 millimeters depth. So it's about 44, 45 millimeter depth.
Okay, so still the fracture is visible, even when the signal noise ratio is quite low. It's around 1.1 decibel.
Yeah. Yes.
Okay. Thank you very much. Yeah, very impressive research.
Thanks.
Thank you very much.
I posted in the chat actually related to your question there. So, and the 50 millimeter distance that we have used there for the setup is a rather extreme case, but it's needed to establish the operational boundaries for this technology. That was part of the main outcome. Can we use it for the typical drilling environments and the parameters and distances, etc. So, and as I state here, there are more typical distance between the sensor and the borehole wall. If you're drilling an in-gauge hole, would be typically below 0.5 inch.
Thank you. Any more questions? Okay, seems we have all questions answered. Okay, thank you again, Dr. Bøklepp and Dr. Indimath. Thank you for your excellent presentation. And if you have more research progress, just let me know, and we can set up another fiche to present your newest result. Thank you very much.
Thank you. And if someone has more questions later on, you can always write to me on this email.
Okay. Thank you. And I will send you the Zoom link, recorded Zoom after this meeting.
Very good. Thanks.
Okay.